Hello, everyone. My name is Sergey Maschenko. I'm at Sharcnet, also based at McMaster University. I'm HPC analyst. And this is one of our regular general interest webinars. So today we'll be talking about debugging on our new clustergram with a debugger called DDT. So the plan is to very briefly go through basics of using DDT. So this webinar is different. I already delivered a few about DDT, and it was always about basics, how to use, how to start DDT, do some very basic things. I'm still going to show some of the basics, but it's mainly targeting people who already know a little bit about DDT but wants to learn some more advanced features. So more than half of my webinar will be dedicated to advanced features of DDT. So I'll briefly walk you through how to use DDT on our newer cluster, Gram. DDT used to be installed on all the clusters, Orca and Monk. Now it's only on Gram. So we'll discuss advanced features of DDT. At the end, there will be time for questions. So let's start with the overview. So I'll intermittently will be showing you some slides and some live demonstration of debugger DDT. So DDT used to be Allinea product from UK when we purchased it more than 10 years ago. Recently, it was purchased by ARM. It's the company making CPU chips. It's a powerful commercial debugger specifically targeting HPC world. So it is installed on many large supercomputing centers in North America and elsewhere. It can do pretty much any kind of debugging in HPC world, serial, multi-threaded, MPI, CUDA, and very importantly, any combinations of the above. So in principle, it could debug a hybrid code consisting of MPI, OpenMP, and CUDA all in one software package. It has all the features debugger needs, of course, basic things like play, pause, step through, setting breakpoints. So all these points have been covered before in our introductory webinars and also in our summer schools where I normally teach a debugging course. But today we'll be discussing about things which I normally don't talk about, like watch points, trace points, and some other advanced topics. Of course, it can display values of variables, but you can also edit them runtime. And the memory debugging module, which is off by default, can be enabled and used as well. Because it's a HPC targeting debugger, there is a lot of functionality for dealing with parallel codes. And what I always like about DDT is how slick and polished the interface is. So there is very easy and very efficient access to different features. Typically, you're 1 or 2 mouse clicks away to access any MPI process or thread, to access any function in any file of your code. You can control execution of processes or threads, either in groups or individually. You can visualize and go in MPI communications, which is very important when you deal with MPI deadlock bugs. It can display values of variables across ranks or threads and many other things. For example, it can do OpenGL visualization of your multidimensional arrays, but we will not be covering it today. This webinar cannot cover everything, of course. Some additional details can be found on our ever-expanding DDT instructions, which can be found on Compute Canada wiki site. Here's the link. It's called ARM software because DDT is now owned by ARM. And the reason it's not called just DDT because it's not only DDT, which is part of the package, but also the parallel profiler map, which we are not covering today. For all the details you ever need to know about DDT, consult the user guide. Just Google it. This is the link I found. Or it's also installed on our Gram cluster. Once you load the module, you should be able to find the PDF file. But I guess Googling it's just easier. So let's very briefly walk through how to use DDT on our newest cluster Gram. As I mentioned, we used to have DDT on Orca and Monk. So if you needed CPU debugging, you would use it on Orca. If you needed to use it for GPU CUDA debugging, you would use it on Monk. Now it's all together on Gram. Neither Orca or Monk no longer have this capability. And there are some differences how to use. For example, Orca and Monk have development nodes, and that's where you would normally run DDT interactively. Graham doesn't have development nodes. It has some other mechanisms I'll be discussing today. For those who never used it, words of caution. First of all, it's a GUI application, graphical user interface application. So you have to ensure that X11 forwarding is enabled. That means when you SSH to a class, you should always add -Y. Also, when you use salloc command, as I will show you later, don't forget to add --X11, small letters. Then you, depends on the terminal you're using. So if you have Windows terminal, the easiest way is to install and run MobExtern application. Just Google it. You need free edition. And it combines many different things, including SSH client and X Windows Server. And it's on by default. Basically, just go to the terminal, type SSH-Y and so on, as I'll show you in a second, and you're good to go. On Mac, they no longer provide X Windows Server, so one has to install a free open source application called XQuartz to have that functionality. And then you use just regular text terminal to do SSH. So as I mentioned, no development nodes in Graham, so you have to use either salloc, that's the default, and for some special situation, sbatch is possible, as I will be showing later today. And this is a summary, very basic summary how to use DDT. How exactly you use it depends what kind of code you want to debug. For all codes, you would, of course, first want to log into Graham cluster. As explained, the critical part, don't forget to add -Y. If you run your DDT and it complains cannot find display, something like that, that means you forgot to add -Y. Or maybe there is something wrong with your X Windows Server on your terminal. If it doesn't complain, you log in, and then depend on your code. For serial MPI, so the default way to allocate resource to use debugger is through salloc command. For those who are not familiar, normally you submit jobs to Graham cluster using sbatch command. With debugging, you want interactive access, and that is provided via salloc command. Salloc is accept exactly the same arguments as sbatch. Just look up inside your sbatch job script and copy one, on a single line, all of those arguments. The same time limit, for example, memory per CPU, that's what you want to provide for MPI or serial code. Number of tasks for MPI code, your account name. So it goes to the next line here, but it should be one single line. Critical part here, because you're going to be using graphical application, don't forget to add --X11. It can be quite annoying because sometimes it's quite busy cluster and it will take a while to get the allocation, interactive allocation. And you want to debug your code, you waited maybe an hour or two, finally you're debugging it, and then you realize you want to use DDT because it's complicated, there is a bug. But you can't, you have to exit allocation, you have to redo it with --X11. So my advice, anytime you do any debugging on Graham, just always add --X11. There is no downside to that. If you realize you need to run DDT, you're good to go. Then you compile the code, and the only extra thing you need to do, you probably know already, for any debugging, you have to add -G. That will generate symbolic information inside your binary. Next, you have to load the DDT module. The package is just one, but there are two different modules. What they do differently, they load different licenses. Because we have two separate licenses, one is for CPU, and for that you need to say module load ddt-cpu. And our CPU license covers up to 512 cores, CPU cores, across all the users on Graham. If you need to debug GPU code, you need to load separate module, as I will show on the next page, next slide. The way you use DDT, you just say DDT space and then path to your code. And you notice probably that I'm not putting any MPI run here, and because DDT has MPI run built into it. You will be able to choose number of MPI ranks from a DDT window. So when you compile, when you debug an MPI code, don't insert MPI run anywhere here. Just say DDT, path to your code, and then optional arguments if your code has any. If you deal with OpenMP, Then there are slight difference in your salloc command. Specifically, now you want to reserve memory --mem for the whole job, not memory per CPU like for MPI. And also instead of number of tasks, you're asking for CPUs per task, let's say 4. Here how you compile an OpenMP code, you just add -q OpenMP with Intel compiler and of course -g. And you load the same module and you run exactly the same way as before. On the next slide, you can see what you have to do if you want to debug a CUDA code. The differences here is you have to add --gres equal GPU column 1. And that command lets you ask for a number of GPUs on one node. Graham GPU nodes only have 2 GPUs, so it can be either 1 or 2. If it's a single GPU code, then you just provide 1. Important point I haven't mentioned, salloc has a built-in limit, time limit. You cannot have it larger than 3 hours. So here I put it to the maximum, 0 days, 3 hours, 0 minutes. I'll explain later what to do if your debugging requires longer runtime. And of course, when you deal with CUDA, you have to also load CUDA module. Then you can compile using standard NBCC compiler. But here the extra point, not just -g for CUDA code, you want to add -G. And capital G corresponds to symbolic information on the GPU side. If you forget that, you will be able to debug the CPU host part of your code, but you won't be able to debug the device part of the code. And this is just the standard way you compile CUDA code on Graham using arch SM_60. And also good advice, unless you suspect that your bug is optimization related bug, at least initially you want to debug your code with -O0. This is 0. That disables all the optimizations. If you do not see bug in -O0, then it's probably optimization related bug. And then you can recompile with -G, -O, let's say 2. It's a bit trickier to debug and optimize code, but it is possible. And then you model load ddt-gpu. GPU license we have is much more modest. It's only covering up to 8 GPUs across all the users of Graham. But you don't get too much usage of it, so it shouldn't be a problem. And then you run your DDT with the code as usual. So I will show how DDT looks like just in a second, but let me start discussing now the advanced features of DDT. So a basic feature will be using breakpoints. I'll show it in a second. And in fact, I think I want to switch now and show a couple of basic points before discussing advanced ones. So I'm switching to the terminal. I already logged into Graham with -Y. So all my X11 traffic should be properly forwarded. I am on a login node. And so I'll be doing some examples from a login node. Or maybe I can use salloc. Give me 1 second. So I will use salloc, but ignore these extra commands. I'm using -A, which is some strange account name. And also I'm using extra --reservation. This is just for this webinar. Normally you don't use reservation and use your normal account name. This is a specially reserved node only for this presentation. And mind you, you have to add --X11, otherwise DDT will not work. So I'm reserving 16 CPU cores on a node. It happens to have a GPU, but we are not going to be using GPU feature for today. Because it is a reserved node, it should be fairly quick. For your normal usage, you might end up waiting. It's quite variable. Sometimes it's almost right away. Sometimes you might end up waiting 1 or 2 hours, something like that. Depends how busy cluster is and how much resources you're asking for. It doesn't seem to work for me. Okay, I'm just gonna check to make sure I'm not having any other jobs which are interfering. I suspect it's just a busy cluster. No, I don't see any. So let me try one more time. It takes more than... So the simple examples I'm going to show you today you can do that even from a login node. In fact, you don't need salloc. Very simple, short MPI, OpenMP examples. You can do that from login node because salloc seems to be having some issues right now. Maybe someone else is doing reservation. Okay. Oh, I was about to kill it. Okay, so finally I got through. It's a bit slow today. I guess very busy cluster. Okay, so that's what you would normally do to use DDT on RAM. You would use salloc. You ask for number of CPU cores you need. The one tricky part, if you want to debug MPI code, you say -N16, so it's a number of tasks, 16. If you debug OpenMP code, you would say -C, whatever number of CPU cores. But I discovered if you say -C, it's 16, you cannot also do MPI debugging. So you actually have to ask separately a salloc command. There is some strange limitation. So hopefully we will not run into it today. So I allocated 16 CPU cores for MPI debugging. And now I can do the simple demonstration of DDT. So I have a couple of codes here. One of them is MPI code called Dynamic Workload Balancing. This is the binary which I already compiled. So what I have to do, I have to say module load ddt-cpu because it's a CPU code. Now I should be able just to say ddt and then the path to my code binary. Again, no MPI run is required. So if you set up X11 forwarding correctly, now you should be able to see an extra window or two popping up where you can enter some information for your debugging. All right. It correctly auto-detected this is MPI code. If it fails for some reason, you can override it here. Normally it detects properly simple MPI or simple OpenMP or simple CUDA. When it's a hybrid, then usually you have to do some extra. You would have to enable, if it's the MPI and OpenMP, you want to make sure these and these are enabled. By default, memory debugging is off, so we will not be using it today, so I'll leave it off. And then all you need to do, just press run, and make sure you choose number of cores you're planning to use, let's say 4 in this case. You just click up, down, or you just type it in. If it's OpenMP, there will be an extra option to enter a number of threads. So I press run. And very, very briefly, here's the basics, how you start using DDT. First, you make sure it correctly connects to all the processes. I'm going to make it a bit larger so it's easier to read. So briefly, what are the basic elements? So DDT consists of a single large window, where there are multiple component windows which are docked. All these windows can be grabbed by mouse and dragged around, placed in different location, or even placed as a separate window. But in fact, the default layout is very convenient. I would advise you against that. Just keep it at default. Works very well. So at the very center, there is a window which shows you the source of your code, and it points to the very first executable line of your main function, basically. This MPI code, this is MPI init. So it is highlighted, both solid horizontal lines and also some coloring. And color means different things depending on the color. This is the source, and you can see also it's nicely color highlighted, syntax highlighted, so it's convenient. And on the left side, you see the source browser. It's an easy one-to-click access to any file and any function inside your program. This case has only one function, one file, 2 functions, so you can easily click between one or the other. And the central window modifies itself accordingly. And on the right, you see values of variables. On the current line, where highlighted, so you see argc has value of 1. You can drag your mouse across multiple lines, and then you see multiple encountered variable values. And right away, I can mention what are these tiny pictograms, which is a horizontal line. As you will see later, it is a pictogram of how values change across MPI ranks. So let me demonstrate that. You can run as an MP3 player. There is a play button, you press play, you wait. In fact, there was a breakpoint, so I right away ran into that. I just removed it. So if you just press and then press pause at some point, and then you just pause at some random spot in your program, here you see the line showing all the MPI ranks, and you have easy one-click access to any ranks. Default is 0. You can go to 1, 2, or 3. As you can see, 0 rank has a pause in one line, others pause in other line. Sometimes one of these squares are not pink, but they're green, which means it couldn't reach that point you want to go to. If it's a parallel program, it's not always possible for all the ranks to get to a specific line in the code. That's fine. You can always press pause, and then everything is paused where it happens to be. And so what you can see here, for example, J1 is no longer just a horizontal line, but it's a broken line. It's a pictogram showing how values vary across different ranks. The other way to look at it, you go right-click with the mouse at the variable name, and then you choose what you want to see. You can compare across processes for MPI. If it's or OpenMP, you can compare across threads. If you do across processes, you see the range of values as a table. And convenient, you see all kind of stats, mean, maximum, range, number of incorrect values, positive, negatives, and so on. If you want, you can also save it as, export it as a file, text file or CSV file. So there is lots of options here. And to finish the basics description, the breakpoint. It's a very important, very basic feature of any debugger. If you want your code to pause once it reaches a certain line of your code, then you just set up a breakpoint. And there are different ways you can do it. Here, for example, you can click with your left mouse button in this field next to the line where you want to pause. And then you can go to, there are multiple tabs here, you go to the breakpoints tab. By default, it creates a breakpoint which is unconditional, so condition is empty here, and it will be acted upon for all the ranks and for all the threads. So any MPI rank or thread reaching that line, which will cause your play button, so you press play here, and anytime one rank or one thread reaches that point, it will pause. As explained before, the rest can be green, which means they haven't reached that point, and maybe they can't because there are parts of the code which are not accessible by all the ranks, which is fine. You can press pause, and then you can see where the rest of the ranks ended up being there, ended up being on other lines of your code. And from here, you can go different things. So by default, you can do like step over, step in, step out operations, and that will apply to all the ranks or all the threads in your code. This is the default focus. But if you switch focus to process, by the way, you see extra line here with threads, but these are all system level threads. Don't ignore those. This is pure MPI code. It doesn't have real user threads. Now the focus is process. So if you click any rank you want, and then you click step next line, actually it happens to step inside a part of the code which is has no debug information. It's a system level library, so it was a bad example. Let's go back to the 0 rank. So you can step to the next line, and it did step to the next executable line because this condition was not true, so it went to this line. So now we have different ranks stuck at different lines because now you can operate them individually. Or you can operate as a group, then DDT will try to synchronize as much as possible every time you make step, but of course with MPI codes or OpenMP it's not always possible, so it will be some kind of not fully synchronized stage. If you have OpenMP or hybrid code, you can also choose focus to be a thread, and then you can have operation on individual threads. So the breakpoints I was talking about, we set up here. You can go to breakpoints tab. If you can set up a condition, so double click here and say you pause there only if j is equal 3, for example, if you want. Or you can remove it if you don't want it. You can specify start over a certain number of occurrences and trigger that many occurrences. Also, you can choose which process that applies to which thread. In fact, you cannot edit that. Instead, if you need that ability, you just disable this breakpoint. You can create fully with more functionality the breakpoints by right-click inside this breakpoints tab. Right-click, add breakpoint, and here you can all information you want. For example, where does it apply? Does it apply to process group or some other groups? We don't have other groups right now, so there's only one choice. But you can apply to all processes or maybe a specific rank if you want. Same applies for threads. So there are some other extra information you can do if you create it through right-click inside the breakpoints tab. All right, that was all the basic information I wanted to show you. Let's switch back to the slides and let's discuss the advanced features. So what are the watch points? What is the different compared to breakpoints? So breakpoints you create to pause your code at specific lines and with some optionally conditional statement. By default, there is no condition, will pause. Anytime rank or thread reaches that particular line of the code, the debugger will pause. Unlike breakpoints, watch points will cause the debugger to pause at any line in the code where variables, which you have to specify, changes its value. This is so-called write type watch point, based on writes to variables. You can change that behavior to read type watch point, and that means every time the code reads value from certain variable, doesn't matter where, within the context where the variable is defined, of course, and then it will pause next time it is read. But it is much more common to use write watch points rather than read watch points. Can be quite useful. For example, at some point inside your code, a certain variable you know becomes bad. It's non-numerical or some wrong value, like negative, for example. For example, you know it shouldn't be negative, it becomes negative. So you set up a watch point and run it, and it will pause where it changes. You can also add extra conditions. For example, you can say it only when it becomes negative. And that can very easily identify part of the code which causing the trouble later on. All right, that was watch points. Talking about trace points, it's yet another concept. In this case, unlike watch points and breakpoints, trace points do not cause your DDT debugger to pause at all. It keeps running, but with trace points, you specify a line in your code, and then it will print the values of all the variables from that line every time it runs through that line of the code. You can specify if you don't want to do it every time, maybe every 10 times or whatever to minimize amount of output. That's the trick to use. So let me just briefly demonstrate watch points. So either breakpoint or watch point or trace point can be set up by going somewhere with a right click on the line of your code. Sorry, watch point you cannot because it's not line specific, but either breakpoint or trace point you can set up it here. Or you can go to the corresponding tab, like breakpoints tab or watch points tab or trace points tab. And then you right click here, and then you have the option to add watch point. And then you usually have more options. You can add more options to your point. For example, which process group, which process, expression you want to monitor. So I want to create watch point for the variable j. By default, it's write only. So every time my code changes the value of j, it will pause. So I created that watch point, and then I press play. So next time j was modified, and I get information. It's a useful pop-up window. It tells you what was the old value of j and what became the new value. Used to be 32,000, became 33,000. And as you can see here, it's because there are multiple ranks reaching the point where the value changes. It will give me a few messages. So there are 2 ranks where a condition was fulfilled, and 2 ranks which is not fulfilled. So that's why they're green. You can always press pause to pause everything. And you can see here it changed because we modified it explicitly. And in the other rank, j changed because it was a buffer. It just received value through MPI receive, and that's why it changed, and that's why watch point was triggered. You can always disable by clicking here, or if you want to delete, you can always delete it. Delete or delete all. And also trace points, you can do it either from a specific line. I think it's more obvious. You go to a line of the code. Let's say, oh, it's going to be too much output. Maybe here. And right-click, add trace point. And it's not going to pause anywhere. Here's a trace point, variable j. And the output will be here, trace point output. And if I press play, it will start printing lines every time it crosses that line. If there are too many outputs, you can make it every 10 outputs or something like that. And you can see every time it reaches that line, it gives a print. It tells you which rank and what's the value of the variable, all the variables in that line. So these are the trace points. You can disable or delete with a right click if you want. So that was two features I discussed, which sort of advanced watch point, trace point. Trace point might not look very useful when you do it interactively, because I think ideally you want to pause and explore what's going on. But it becomes invaluable if you use offline mode of DDT usage, as I will show you in a few minutes, where you lose interactivity. And then basically you can't really do much debugging unless you set up trace points, so it does save values of variables at certain lines of your code at certain moments of time. And then you can analyze it offline. I'll show it later. Another advanced topic, how do you debug hybrid codes? And I'll give you just one specific example, MPI plus OpenMP hybrid code. Other possibilities are MPI plus CUDA, or even MPI plus OpenMP plus CUDA. It's all possible to debug with DDT. Of course, even vanilla parallel programs like MPI, it's already hard enough to debug. Hybrid is even harder, so DDT becomes very invaluable tool. Among the conveniences DDT brings for hybrid code debugging, there is an easy way to switch focus from MPI ranks to CPU threads to GPU threads. I already showed you how you can switch MPI to threads and back. And also you can make breakpoints and watch points specific to threads. And you can display variable values across all ranks of threads. I already showed you for MPI case how you can do that. So let's do a quick demonstration of a hybrid code. So I'm going to kill DDT window now. I have a hybrid code, which is called hybrid. What it does is finds the value of the largest prime number within a given interval. And it's a combination of MPI at high level and OpenMP at low level. So let's try, I already compiled it. So let's try to debug it using DDT. As I mentioned before, for hybrid codes, DDT normally do not or does not detect automatically all the flavors you're using, like that it's both MPI and OpenMP. As you see, MPI is easy. Once it sees linked to dynamic MPI libraries, it knows it's MPI. For the hybrid code, OpenMP sort of fails, so you have to manually enable. So we'll be running this hybrid code with 4 MPI ranks and 4 threads. I never tried this example from under salloc. Let's see if it's going to work. It did work for me under login node. So let's try it now. It will complain. It doesn't think it's OpenMP, but it's hybrid. You know it has OpenMP and MPI, so just say yes. Override that. So now we have, as usual, the very first line of your code, which is MPI part. But I know there is a function, the prime search function, which has pragmas inside. In my experience, it's easier, or the only way to debug OpenMP multi-threaded code is not by step, but you either set up a breakpoint inside parallel region, or there is another also option, right-click on a line in your code, and then choose run to here. So what's the difference? So when you say breakpoint or set a breakpoint, the very first MPI rank or thread which reaches that line will cause debugger to pause. Run to here has different functionality. It will not just pause there, it will try to synchronize as much as possible all your ranks and all your threads. Of course, in a real parallel application, it's not going to be possible usually to synchronize everything. So it will try to do its best. So it might take longer actually to do run to here. So instead, I just need a breakpoint, and I press play. So it paused on that line. And because the focus is groups, all I have as before, just control, or you can go to different MPI ranks. And it did manage, in fact, synchronize all of them. They're all in the same line. And then you can switch focus to thread. So now you see extra line of threads. As I mentioned before, there are a few extra system level threads which you have to ignore, but the 0 to 3 threads should be the real user threads. And you can now single click brings it to different threads inside a specific rank, which is 0. So first you choose rank, and then you can choose a thread you can debug. And because the focus is thread, now we can operate individual thread inside individual rank. So if I click step, you see there are multiple lines having different color. So other threads are still here, but I'm operating individual thread, and now it's desynced. If I switch back to previous threads, you can see they're still on the original line. The rest is, the thread number 3 is here. I can switch back to the process, and then I think it should operate all threads together as much as it can. But I guess because we already desynced the system, then it becomes kind of confusing. So if you want to operate all threads together, you probably first run there with the breakpoints and then sort of do that default behavior. Or you can operate everything, all the ranks and all the threads together as much as synchronously as possible. But again, you cannot really ensure synchronicity in a complex parallel code. Different ranks will be at different states, but DDT tries to synchronize as much as possible. All right, so enough about that. So it was a quick demonstration of a hybrid code, and hopefully it gave you enough information so you can do it yourself. And now let's talk about the main topic for today. So what to do if your code has a bug which is triggered sometime quite randomly, and most likely beyond the 3-hour limit of salloc. So you can no longer use salloc to do interactive debugging with DDT. What to do with that situation? If it's not random, if it's predictable, the best solution is run the code, see where the bug happens, and then use checkpointing to pause the code right before the debug happens. And then you use salloc and you start from that checkpoint and you easily reach the bug point. But if the bug happens at some random location, unpredictable, and often beyond the 3-hour limit, what to do with that? And here I give a few, I believe 3 different options you can use. The best one is the advanced option DDT, which is called attaching to a running job. I'll show you in a second how to use it. Basically, what you need to do, you compile your code with -G, make sure it is has symbolic information ready for debugging. But then you don't run it through DDT. You submit it through SBatch as your regular jobs. Once it's running, you can launch DDT on a login node. Just say module load ddt-cpu, for example. Say DDT without any argument. And as I will show in a second, then you can see the option attaching to a running job. It will need to know which nodes the running job is using, and you could get that information by running sq command. That there will be 1 or more nodes the job is using, and then you will enter it inside the DDT window, and then it will automatically attach to a running job. Sometimes you have to say which binary you're debugging, provide the name of the binary, so it can find that binary on the remote node. And then you can debug it as usual. So your program will pause, and you can debug as usual. You can press play, and then just wait for the bug to happen. So in this case, because the job is consuming cycles on a regular partition, non-interactive, it doesn't have the 3-hour limit as salloc has. So in principle, it can run way beyond the 3 hour. There might be a twist, sort of a caveat on a login node. If any process consumes more than certain amount of resources, it's 1 CPU hours in fact, it may get killed. So I haven't tried it, but I don't think DDT consumes a lot of CPU cycles on a login node. So in principle, should work for multiple hours jobs. but it's something which needs to be tested. So let me demonstrate that feature. So I'm going to kill. So for this, I need to submit a job. And I'll be just using my SL, but normally do it from login node. So I already have a job script. It's called, let me see, job MPI. I'll show you what's inside this job script. Usual stuff. I'm going to be showing the MPI code debugging. So I'm using srun. In my experience, this technique does not work if you do not provide full path. So instead of relative path, you say srun and then full path to your binary code. In my experience, that's what you need to do attaching to a job. This binary was already compiled with -g, so it has all the symbolic information. So let me submit this job. And I will need to submit specific reservation. Ignore that part because you don't do that for normal jobs. You just use your regular sbatch command. But I have to say sbatch, I have to say special account name, and I have to say special reservation name, just for the purpose of this presentation, and then the path to my job script. So it should be running pretty much right away. So then I do sq command to be able to see which nodes I'm using. So this is the job MPI job I'm running. It just happens to be local, which might be slightly confusing. So what if I switch to login node to make it like more realistic? So I do SSH ram. I just open a separate window, second terminal. No, sorry. Oh, it did work. All right. I didn't put compute canada.c. You normally should do that. And login is a little bit slow. All right. And then I say module load ddt-cpu. So I have a running job, and I'm on a login node. I know which node I'm using, GRA956. So I'm going back to my login node. I say ddt-cpu, no arguments. Sorry, CPU. Just DDT. Confused here. So module load ddt-cpu, and then you run DDT without any argument. But you don't. So here you don't run anything. You use the second option, attach. You might not be able to read, but it says attach to already running program. All right. So first thing, it tries to find a process which you run on a current node, which is login node. So because I don't run anything, it finds nothing. And then it lets me add a host. I already had some old host here. I'm going to remove it. I'm going to add the host I know my job is running on, GRA956. Okay. Okay. And I think it also remembers last binary name I was checking. It was hybrid, but in fact, the binary I'm running is dynamic workload balancing. So it's DWB. Yeah. So it already can see that on that node, there are 4 MPI ranks. So I select all of them, and then I press here, attach to selected processes. And then what happens, I connect to my running job, which I run regularly through sbatch, and it's already paused, but in my experience, it usually is paused and it's a system level library, so normally you don't see any text here, which is fine. What you have to do, you press play, and if I could pause in the very first breakpoint I had, and then you can debug as usual. You don't need to have breakpoints. You press play and then pause, and right away you will end up in a regular part of your code, not system library. And then you do absolutely the same style debugging. You can press play and wait for your bug to happen. You can set up watch points, breakpoints. You can do any kind of debugging tricks I already described, or there are some extra in the manual. And the beauty here is we are not limited by 3-hour SLOC limit. You're running on a regular partition, but you are debugging inside DDT by means of attaching to a running job. When done, you can kill the DDT process here, and maybe sometime later you can repeat. You can again attach to a running job. if you are got satisfied that there is no bugging from situation, maybe it's going to happen later, you can kill the process and reattach at some point later. You can do it as many times as you want. So hopefully that was clear demonstration of how you can attach to a running job. And there are two small topics which will not take much time. By far, the most convenient trick to use if you want to debug a job which has a bug beyond 3-hour limit of a salad by attaching to running job. But there are two other tricks you can also use for limited types of situations. For example, if you have a segfault and your job generated as core files. By the way, I tested on home file system, core files are not created. You should run your job as is normally the case, either on project or scratch file system. And then it does create large one or more core files. And if your code was compiled with -G, those core files will contain symbolic information, and you can analyze the final state of your code at the crash time by loading the core files in the debugger. So let me demonstrate that feature. So I'm going to a project file space where I already have core files. Yeah, so I ran a program here and it generated this core file. So what you do module load ddt-cpu, which I already did. Then I say ddt, no arguments, just ddt without any arguments. Again, for a simple quick test, you can do it from login node, but normally you want to do debugging using as-salad, as I'm doing right now. So there was option number 1, debug a program. Second, we just saw attaching to running job. And third option is open core. When I open core, it remembers the cores I opened last time. So this is the list. These are core files inside. If you don't see them here, you just say add, and then I choose directory and I choose the core files. And then you have to provide full path to the binary. So core files don't know where the binary is located. So you have to, it's an extra argument. Again, you open, make sure you point to the correct binary file. So when both conditions are met, you can say OK. And then it will open the familiar interface, debugging, but pointing to a specific line of your code where the bug happened. It actually might be I'm pointing to a wrong. Anyway, so here's this is the idea. So it will open the debugger pointing, and the line will be pointed to the correct line where the crash happened. I suspect I opened wrong binary file. That's why I don't see segfault situation. Segfault is typically happens when you write beyond array boundaries. And this example, I believe, had that. I just don't see it here. So that was, obviously, it's not very useful, only for segfaults and only when you already have crash files, core files. And they're only useful if you compile your code with -G before you run your code. And the final point I want to talk about in terms of how to debug large jobs, you can also try offline debugging. Offline, which means it's non-interactive. You submit as batch jobs, non-interactive jobs. Of course, it is much more limited. When you debug, you really want interactivity. You want to be able to click through different lines of the code, to step through them, to look at different variables at different moments of time. But as a last resort, you can try this as well, if nothing else works. To use DDT in offline mode, you submit a job script through as-batch, which has this line, the last line of your job script. In fact, I now realize you should probably add DDT module load ddt-cpu or -gpu. There will be 2 lines in your job script. I suspect if you load and then submit job, it will be loaded automatically. But to be on the safe side, probably should say module load ddt-cpu, and then you say ddt --offline. And then you have to provide a lot of different switches. For the full list, please consult the guide, DDT guide. I just give you an example. If it's MPI code, you say -n and the number of MPI ranks you want to use. At the very least, you probably want to say --snapshot -interval equal number of minutes. In this case, every 10 minutes, the code will save variables, different values in the current context it has at that point in time to a file. It's not super useful, but somewhat useful. And then the path to your code. Probably much more useful to use or set trace points. So there is a dash trace, and etc. Look up information in the manual. And then you can specify which lines of the code and which variable values you want to be printed every time code passes there, or maybe every 100 times the code passes that line. So as you can see, it's quite limited. It's non-interactive, but it may be good enough for you to identify the bug. So that finishes the official part of this presentation. Thank you very much for your attention.